Okay, so the induced EMF due to a change in flux is equal to negative delta phi over delta t. Now, what if I have a circuit set up where this is a wire and this is a wire, and they don't have any insulation on them, so they're just bare wires. I put a resistor here, maybe a light bulb or something, but something that's a resistor. And I'm going to take and put a bar, like a bar of copper or something like that, on top of those bare wires. So now there is a metal connection all the way around. Okay? But this bar can slide along those rails or slide along the lines. Now let's take and stick it in a magnetic field. So these big red X's represent an external magnetic field, a magnetic field created by something else. It's just all over the place in here. Uniform magnetic field, big giant X's. Okay, so let's take this bar and let's move it to the left. What's inside this bar? What is it made of? Okay, what are its pieces? Go small. It has protons, electrons, and neutrons, right? And so just like in the mechanical universe video when they had the piece of wire moving in the magnetic field, if this piece of wire moves to the left and a magnetic field directed into the page using the right hand rule, right? Everybody uses the right hand rule. The positive charges in the bar would be forced which way? Down the page. Where would the negative charges in the bar be forced? Up. So we would have a separation of charges. We would have positive charges pushed down to this end, negative charges pushed up there. If I have a separation of charges, I have a potential difference or voltage. So what does the bar behave as? A battery. So which way does the current run? Conventional current, so from positive to the negative side. So your current would run from the positive to the negative side. That would be the direction of the current. So as this guy is moving, let's say that the length of the bar is L. And as it's moving along, it's going to move to some new location, maybe like right here, where it has gone a delta X. Okay, so we'll call this little distance a delta X, a little change along there. So what's changing is the, for the flux, BA or theta? The area is changing. So the magnitude of the EMF would be equal to the absolute value of delta phi over delta t. So that would be B delta A is the angle between the normal to the plane of the loop and the magnetic field changing? No. So the angle is 0, so we got a cosine of 0, and then over a delta t. So for our area, how's our area changing? So our area is changing by L delta x, so B L delta x over delta t. What's delta x over delta t? Meters per second, which is a measure of what? Velocity, BLV. So the magnitude of the motional EMF is BLV. Magnetic field, the length of the rod, and the speed of the rod as it moves through the magnetic field. And I don't care about the polarization, the sign on it. We can determine the sign by using the right-hand rule in this case.